This talk focuses on how to make the most out of SIMD on ARM Arch64. Traditionally, optimization by the code owner or developer in code design approach tests the most widely used options such as O3, FastMath, MCPU, MTune. On LLVM, other optimization can be specified with -LLVM to specify whether scalable vectorization must be used or if the compiler must use a specific fixed size vector bits. On the top of this compiler option, the developer can opt for adding specific annotation called pragmas onto each loops. This pragmas allows to indicate precisely the optimization that must be applied by the compiler to a given loop nest. To exploit the best of the Arch64 core that are highly out of order, two specific pragmas can be used. Interleaving count that helps to unroll a specific loop in a way that is suitable for out-of-order processor, and vectorization width that helps to specify the number of elements that can be processed simultaneously by some SIMD units. These two influential parameters help to saturate pipelines of Arch64 processor. As you can see in this picture, interleaving and vectorization factor are two orthogonal concepts that can be combined. The main problem is that this parameter can only be specified through pragmas, which is both error-prone and time-consuming. Therefore, this work introduced two new LLVM compiler options for both C++ Realm and Fortran Realm that allows to have a systematic exploration at application level. The underlying idea is to suppose that most of HPC or AI applications deal with a single data type, for instance double, and that consequently there exists some best combination between interleaving and vectorization factor. The technique presented in this talk is especially relevant for applications with flat profiles that are hard to tune. With this new option we introduce into LLVM, one can now consider a one-shot exhaustive exploration. Such exploration can now help to investigate combination of all existing compiler options with some options that were only previously activable with pragma at only the cost of one execution time. With all of this, the paper presented how to retrieve exhaustive comparison like the one presented in this slide. Red cross represents LLVM default choice, and all data points on the left represent all the gains that can be obtained with our approach. This work opens a wide range of opportunity to fine-tune application and optimize compiler heuristics. While this work focuses on Arch64, which is the core of SiPearl CPU, this technique is applicable to other architectures like RISC-V or x86. Don't hesitate to reach out to the main author, Serval Martino Lagarde at SiPearl or me.